Talk about the ratio test. So last time we talked about the Cauchy Hadamard test, which detects the radius of convergence of a power series. And the key to that test is the ability to calculate a limb sup as n goes to infinity of an to modulus an to the 1 over n, where the an's are the coefficients of a power series. So we have an arbitrary power series an z minus a to the nth power there, and we're trying to detect its radius of convergence. That requires us to calculate this limb sup. Now the limb sup is always going to exist. It might be infinite, it might be zero, but we will get some limb sup and then we will get some radius of convergence here. And so the Cauchy-Hadamard test is a very powerful and important tool that describes the level of convergence of an arbitrary power series. Now, in practical terms, so that's the theoretical value. In practical terms, it can be rather hard to compute the limb sup of the modulus of these coefficients raised to the 1 over n power. That can be very difficult to do. And so it's useful to have some practical tests that are a little bit easier to compute. And so a practical alternative to the Cauchy-Hadamard test, which is effectively a root test, is to apply the ratio test. So let's look at the ratio test here. The ratio test also introduces an arbitrary power series and tells you to compute something completely different. It tells you to compute this r, which is 1 over the limit, not limb sup, the limit as n goes to infinity of an plus 1 over an modulus. So notice that the limb sup has changed to a limit, and the nth root has changed to a ratio here. Now, if r equals this, that is, if that exists, basically, then r is going to be the radius of convergence. So basically, we're just swapping out a limb sup for a limit and swapping out an an to the 1 over n for a ratio between consecutive terms. This can be much easier to compute. And I want to show you an example that makes it plain why we would want this ratio test instead of a root test. So let's look at an example first. So an example of this. So if we have f of z is going to be the summation n equals 0 to infinity of n z to the n. This is a very simple power series, and we would expect to be able to analyze it easily. Now, if we take the limb sup of n to the 1 over n, well, it's not all that hard, but it's kind of hard to compute. But on the other hand, if we take the limit of n plus 1 over n, that is the ratio between consecutive terms, and I'm dropping the modulus signs because I know that these are non-negative integers here. So if we take the limit of this, then, well, we get the limit of 1 plus 1 over n, which is 1. Take the reciprocal of that, and you get 1 is the radius of convergence. So you can see this limit is very easy, but the limit of what is effectively the root test here in the Cauchy-Hadamard statement is harder. I mean, I'm not saying this is super hard to do. You take e to the log of both sides and you simplify and you use continuity, but it certainly is harder than this. So, so you can see this is an example where we would like to have the ratio test. So the ratio test is more convenient than the root test, right? And so why don't we just have the ratio test? I mean, if it's so much easier. I mean, there are cases when the root test is super easy, but those are also cases when the ratio test is super easy. So why don't we just rely on the ratio test? It's the meaning of this if in both statements. If r equals this is a very weak condition because it's a limb sup. And there's always going to be some limb sup for this sequence. If r equals this limit is a very strong, well, 1 over that limit, that's a very strong condition, and it can sometimes just completely fail in the sense that either the ratios themselves don't exist because that denominator an is 0, or the ratios exist but the limit itself doesn't exist because they flop around and they take all these different values and there's no limit. So in either of those cases, the ratio test will simply fail to compute anything. But in those very same cases, then the root test will succeed. The Cauchy-Hadamard test, which is effectively the root test, will succeed and you can calculate. So this isn't just theoretical. There are some important practical examples that work this way, including the trig functions sine z and cos z for complex numbers. They have terms that alternately are equal to 0. And so if every other term is equal to 0, and you try to take the limit of these ratios, half the ratios are going to be 0, and half the ratios are going to be undefined, and you certainly can't take the limit of that. So the ratio test is incapable of calculating the radius of convergence of something like one of these trig functions because every other term is 0. But the root test will not have any problem with that. Well, I mean, it's not an easy calculation to be fair, and there are some tricks that we'll see later for how we actually calculate the radii of convergence of those trig functions. But first, we'll have to define them. And so, but that's the topic for another day. What we're going to do today is we're going to prove the ratio test. So I want to talk to you about how we prove the ratio test. The secret to proving the ratio test is to prove that this R and this R are the same R under the assumption that it at least exists. That is, you get the luxury of assuming that this ratio exists, which means you've effectively assumed that all these modulus ANs are non-zero. You've effectively assumed that this limit exists, and then you have this R, and it exists. The secret is we're just trying to prove that this R is equal to this R over here in this other theorem statement. That's all that really needs to be done. So all we really need to do is prove that whenever you have any sequence of complex numbers an plus 1, then when you take this limit, then it works out to be the same thing as if you take this lim sup. But wait a minute, these ANs that are appearing in both theorem statements are always appearing inside modulus signs, which will yield non-negative real numbers. And so really what we can do is we can abstract this a little bit and think of that as a statement about non-negative real numbers. We can forget all about power series. We can forget about radii of convergence. We can just think of this as an abstract statement about limits and lim sups of non-negative real numbers. And they're not just non-negative real numbers, because once I assume that this limit exists, then I've assumed that an is not 0, because otherwise I couldn't divide by it. So I can assume that these are positive real numbers. So in other words, I can abstract away all the power series, all the z's. I can abstract away the fact that the ANs are complex numbers, and I could just work with a sequence of real numbers, which are the moduli of the ANs, and I can assume that those real numbers are positive. So that's what we're doing here. Now, it may be slightly confusing. In this claim, I'm referring to ANs. These ANs are the moduli of these ANs. So that's why I'm hypothesizing that they're a sequence of positive real numbers. All we really need to do to prove the ratio test is to prove that this R equals that R. And all we really need to do to accomplish that is to prove that if we have a defined limit of ratios, and that's equal to L, then the limit of the roots will also be equal to L. Now, you might say, oh, I forgot the lim sup. And in a way, yes, it should say lim sup. But if the limit is L, then certainly the lim sup will be L. So if we're able to prove this first claim, then we'll apply it to the moduli of the ANs above, and we'll end up proving that the limit of the moduli of the ANs is equal to that same value. And so then the lim sup is also. So the plan of approach here, we're going to prove claim 1 and use it to support the ratio test. But claim 1 is kind of annoying because we have, again, these nth roots and these ratios, and it's easier to just take logs of everything. And so claim 2 is basically the corresponding statement after logs have been applied to everything. So the BNs are secretly here the logs of the ANs, and the K is the log of the L. And what we're going to do is we're going to prove this statement, which is basically the corresponding statement after logs have been applied. And then we're going to use that together with logs and exponentials to support this statement. And then we're going to use this to support that statement. So the key here is we're going to begin with claim 2. So let's begin with claim 2. All right, proof of claim 2. Now, even claim 2 as phrase is a little bit hard to prove. It's a little bit fiddly. So what we're going to do is we're going to assume for simplicity that K is equal to 0. Now, obviously, that's not the general case, but then we'll be able to prove the general case from that specific case. So case A is when K equals 0. So what are we saying then? We're saying the successive differences between these terms is getting very, very small. It's approaching 0. And then we're trying to show that the term divided by n is going to also approach 0. So if K is 0, then because the limit of Bn plus 1 minus Bn is equal to 0, we can choose some cap n1 so that for all n greater than or equal to cap n1, then we have that successive difference really rather small. So what we have is bn plus 1 minus bn absolute is very small. And how small do I want it? I want it smaller than epsilon over 2. So I'm going to get those differences very, very small. So if k is 0, then the limit of these is 0, and I can get them eventually as small as I like. And so I'm invoking the definition of the limit here. So we'll choose n1 so that that's true. And now we'll need another choice of n. So I'm gonna put placeholders here for a choice of n2, and I'm gonna choose n to be the max of n1 and n2. And then I'm gonna let n be greater than cap n. So I'm gonna postpone the reveal about what other requirements we need to place on this little n, but I want to make sure that the structure of the proof makes sense at the beginning. So now we're going to take a large value of n, and then what are we trying to do? We're trying to prove that this limit is equal to 0. And so I need to control the absolute value of this thing. So then bn over n absolute is the thing that I need to get epsilon, I need to get less than epsilon. I've noticed that I didn't begin with here, let epsilon be positive. Maybe it was understood. So we've got a positive epsilon, and we want to show that this thing is going to be less than epsilon to establish that this limit is equal to k. And again, k is 0, so that's legit. So this thing is going to be controlled by comparing b sub little n to b sub n1. And so this is going to be b sub little n minus b, oops, I wrote that wrong, minus b sub n1 plus b sub n1 over n, absolute values, of course. Now, okay, so now what? Now this fraction is going to split, and then we're going to apply the triangle inequality, and that'll give us b sub little n minus b sub n1 absolute over n plus, and then we get b sub n1 over little n. So I'm comparing b sub little n to b sub cap n1. Now, and that's less than or equal to. Now, how are we going to control this term? Well, this term is a difference between two terms in the sequence b, but they're quite distant. It's b sub n1 being subtracted from b sub n, which is much farther down in the sequence. So that's a difference between two terms, but you can regard a difference between these distant terms as a sum of many differences between consecutive terms. And so this is really equal to, well, I'm not going to write all of those consecutive terms, but if we have a difference between these distant terms, then that's a sum of a bunch of consecutive differences between consecutive terms. And each of those consecutive differences is controlled by this line. And so what we get here is we get epsilon over 2 times how many of them there were, and there were exactly n minus n1 of them over n. So basically what I'm doing, I'm taking this long distance difference and translating it into exactly this many short distance consecutive differences. Each one of those is controlled by epsilon over 2. And now you can see I've dropped the absolute value signs here because, well, I know that everything that I've written is positive. And then this term I'm simply going to rewrite. I'm not going to worry about that yet. B sub n1 over n. But I still need this module, absolute value. It's absolute value because these are real numbers now. I shouldn't say modules. All right, now what do we get from this? This is still kind of a mess, but notice that little n minus cap n1 is at least not as large as little n. So this ratio here is bounded by 1, and so I'm just going to bound this term with an epsilon over 2. So that's actually strictly less than epsilon over 2 plus absolute b n1 over n. Now, so I've got kind of half control here over bn minus n. I've split it up like this and gotten control over half of it. How do I get control over bn1 over n? Well, the fact is n1 is a fixed constant. And as little n, And so b sub n1 is a fixed constant too. And I don't know what its value is, but as little n gets larger and larger and larger and larger, eventually it'll be much, much larger than the value of b sub n1. And then this term can be made less than epsilon. So how large does little n have to be in order to completely destroy this term and leave us with an epsilon over 2? It needs to be equal to b sub n1 to cause the cancellation divided by epsilon over 2. And that's what we're going to choose n2 to be. We're going to choose n2 to be b sub n1 divided by the quantity epsilon over 2. And I know I could simplify that fraction, but that's actually just exactly the form that I want it in. Because now, once n2 is chosen to be that, and n is chosen to be the max of the two, and little n is larger than n, and therefore larger than that, then this term is definitely going to be less than b sub n1 divided by that whole thing, which will simply drop an epsilon over 2 in the numerator and give us epsilon over 2 plus epsilon over 2, which of course is epsilon, which is what we need. So this demonstrates that at least if k is 0, if the limit of the successive differences is equal to k, then the average, well, this is not really the average, then bn over n is also in the limit equal to k. So bn over n is less than epsilon. So that demonstrates the claim in the case when k equals 0. Now, if k is not 0, then we still have a little bit more work to do. So let's figure out what we need to do in the case when k is not 0. So we'll call this case B, and the definition of the case will be that k is not 0. Now, what we're going to do is we're just going to cleverly rig this so that we can compare it to the case when k equals 0. So let's let c sub n be b sub n minus nk. So the whole point of this is that we're going to rig a different sequence so that its successive differences will actually be equal to a different value, namely 0. So then what does this tell us about c sub n? So let's do the limit of the c sub n's. So the limit of c sub n plus 1 minus c sub n is equal to, by definition, the limit of b sub n plus 1 minus n plus 1k minus b sub n plus nk, which is equal to the limit of b sub n plus 1 minus b sub n minus k. That's as n goes to infinity, which is k minus k, which is 0. So the point here is we're comparing the sequence b sub n to a new sequence c sub n, which is just about the same, except it's sort of shifted by this linear function nk. And what happens is then the successive differences between this auxiliary sequence cn, well, they go to k. And that means that this claim to case A applies to the new sequence c sub n. So then by claim to case A, then what do we conclude? We conclude that the limit, let me write it in the next line. What do we get? The limit of c sub n over n is equal to 0. Why do we get this? Because we know that this limit is equal to 0. And so we're applying case A to the auxiliary sequence Cn. So we get that this is equal to 0. So what does that mean? Well, that is the limit of, what's the definition of C sub n? It's B sub n minus nk. And so we'll fill that in, and then over n is equal to 0. And then another that is, now just simplify this fraction, the limit as n goes to infinity of b sub n over n minus k is equal to 0. So the limit of b sub n over n must be equal to k as n goes to infinity. Just add k to both sides, use limit laws. So, so there we have it. If b kind of has an inconvenient, if the successive differences between b are inconvenient, then correct them and use case A, and you'll get the result. So that establishes claim 2. Now we need to use claim 2 to establish claim 1, and this is basically the use of logarithms and exponentials. So let's do that next. So let's start with, so proof of claim 1. So what do we get? What are we given here? So assume that the limit as n goes to infinity of an plus 1 over an is equal to L. Now, in this case, remember, the an's are positive real numbers. So we'll take logarithms of both sides. So ln of the limit, and I'm going to do this carefully because I'm going to have to apply the continuity of the logarithm, and I want to make sure that I'm not making a mistake when I do so. So that's going to be equal to L to ln L. So now this limit is presumed to exist, and the logarithm is a continuous function. And under those conditions, we have proven that the logarithm can be moved inside. So applying the composition law for the limits, we get that the limit as n goes to infinity of the logarithm of an plus 1 over an is equal to the logarithm of L. So it's important here that we already assumed that this limit existed and that we know that the logarithm is a continuous function. If you're worried about the logarithm and we haven't defined the logarithm yet for complex numbers, it doesn't matter because we're using the real logarithm function here. And then we get to use the properties of the logarithm. So we know that the limit as n goes to infinity of the logarithm of an plus 1 minus the logarithm of an is equal to the logarithm of L. And now this is bn plus 1, this is bn, and this is k. So we get, that gives us the if part of claim 2. So from claim 2, we get to determine this. So by claim 2, what do we get? We get this. So we get the limit as n goes to infinity of 1 over n times now its logarithm of an is equal to, well, the same value, the logarithm of L. And now that's not what I'm looking for. I need to get rid of the logarithms somehow. Now I'd like to sort of, if you just pull out the logarithm, then that could potentially be an error because if I pull out the logarithm, I don't already know that the limit of 1 over n an, sorry, if I first use the rules of logarithms and then just pull out the logarithm, I don't know that the inner limit is defined. So instead of pulling the function out to create a limit on the inside that I don't already know is defined, I'm going to just exponentiate both sides, which is effectively the same thing. And then I'll have a limit that I know is defined. Like at this point, I know this limit exists. And so if I can apply any continuous function on the outside, then I'm safe using the composition law for limits. But if I'm taking a continuous function out now, then I don't upfront already know that the resulting inner limit exists, and so I could potentially be making a mistake. So that's why instead of trying to pull the logarithm out, I'm going to push an exponential function in. But of course, it's the same thing. So then e to the limit of, and now, well, yeah, let's just do the rule of logarithms at the same time. This is the logarithm of an to the 1 over n. So logarithm of an to the 1 over n is equal to e to the natural logarithm of L, which of course is L. So now this limit is known to exist, and this function e to the x is a continuous function on the real line. And so, so we're okay passing this function inside. And so that gives us the limit as n goes to infinity of e to the log an to the 1 over n and that of course is L, and then everything cancels on the inside of that limit. And the cancellation doesn't actually involve the limit here, so we don't have to worry about the relationship between the cancellation and the limit. And we get this thing is equal to L, which is the desired conclusion for claim 1. So that's claim 1. So basically, by careful, judicious use of exponents and logarithms here, we cancel what we need to cancel, and we deduce claim 1 from claim 2. Now, finally, just for the record, let's write down that the proof of the ratio test is that we apply claim 1 to the absolute values of the ANs in the ratio test and invoke the Cauchy Hadamard test. So that proves that this limit, which is asserted in the ratio test, is actually equal to the limit which appears in the Cauchy Hadamard test. And so we just lean on the Cauchy Hadamard test to conclude that R is the radius of convergence with everything that that entails. And that is the proof of the ratio test.